Today, I'll present you a novel solution to implement the geometric algorithms while combining robustness and efficiency. So this is an outline of the talk. I'll start with a brief description of the context that motivated my work. Well, when we model solid objects, and in particular free-form solid objects, we typically deal with polygon meshes. And as you know, this is an extremely flexible representation, but for some important algorithms, polygon meshes require a tricky treatment. These include mesh offsetting and Minkowski sums, mesh repairing, Boolean operations, or even volume meshing when the boundary of your domain is not well defined. When we deal with these difficult algorithms, we typically need to choose we want to be robust and then sacrifice efficiency, or on the contrary, if we want to be fast but occasionally fail or produce wrong results. We have examples of robust algorithms implemented in Siegel and Tetwild, while most commercial tools are not that robust in some extreme cases. So let's see why robustness is that an issue. The problem is often due to a naive use of floating point arithmetic to resolve critical geometric predicates. Imagine, for example, that our algorithm our algorithm needs to determine whether a point R, as in this image, is on the left or on the right of a straight line by P and Q. In formulas, this is equivalent to determining the sign of this expression here. Okay, if we slightly move R off of the line, the image of the sign under floating point calculation is shown in this picture here. So, well, the appearance of these zeros, these yellow points here, is expectable, but the real problem are these little guys here, because in these cases, we are, our predicate calculation is returning us the fact that R is on the right of the line while it is actually on the left, and vice versa. And these wrong answers can easily break algorithmic invariance and hence lead to wrong results. But in the worst cases, these can even lead to infinite loops and program crashes. So how are these problems dealt with in practice? Well, the easiest solution is to replace floating point numbers with the exact number types provided by existing libraries. There are plenty of these tools around the internet. Well, these libraries guarantee robustness, and authors of the libraries themselves claim that the slowdown with respect to floating point calculation is about 20x. Actually, in practical conditions, the slowdown can be as much as 2 orders of magnitude, which makes most algorithms actually impractical. Fortunately, in most cases, we just need to guarantee that the program flow is correct. And to achieve this result, floating point arithmetic can be still exploited. Well, if the expression of our predicate is evaluated using floating point arithmetic, but its value is far enough from 0, then we can guarantee that its sign is correct. The fact here is to establish how far it must be to have these guarantees. So comparing the evaluated expression against a threshold value is known as arithmetic filtering. If the comparison is true, so the magnitude is larger than the threshold, we say that the filter succeeds and the sign of the expression is guaranteed correct. Otherwise, we need to switch to a more precise computational model. There are many ways to calculate the threshold. For example, in a static filter, the threshold can be calculated once for all, and it is independent of the actual predicate's input. So this is very fast, but fails a lot. On the contrary, in a dynamic filter, input values are used to calculate tight thresholds at each predicate call. This is much more precise, but unfortunately, it has an overhead on the predicate evaluation because the filter must be calculated all the times. As a good compromise, semi-static filters are combined a static part computed once for all and the dynamic part that can be computed at each call, but very quickly. So these are a good trade-off. The fact is that all these technologies are from fast but imprecise to slow and precise. So a good idea is to cascade them one after the other. So we use the static filter as a first attempt. If it doesn't work, we use a semi-static filter and then a dynamic filter. And as a last attempt, we can revert to exact arithmetic. All of this machinery works if the input to the predicate is exact. So what happens if the input is affected by a potential round-off? For example, how can we know whether the circumcenter of a triangle is on the left or on the right of a straight line? The fact is that the coordinates of the circumcenter must be calculated or constructed. And such a construction may introduce a round-off error because we are using floating point arithmetic to do the calculation. And this error may spoil all the guarantees that we are given by our filter. To the best of my knowledge, the best solutions so far to these problems are provided in Siegel, which I consider to represent the state of the art. And for problems that do not require predicates and intermediate constructions, Siegel employs a multi-stage filtering approach, such as the one I just described, which is nearly as efficient as naive floating point arithmetic. Conversely, if constructions are used, Siegel employs lazily evaluated exact expressions, which means any intermediate value is constructed using interval arithmetic, and the same interval arithmetic is used to evaluate the predicate expressions as well. So if the resulting interval contains the zero, then its sign is ambiguous, and the predicate is re-evaluated using exact arithmetic. This approach is relatively efficient, but requires storing the whole history of the construction for each eventual exact re-evaluation. And this has, of course, a cost. So the concept of indirect predicates I am presenting today allows to fully exploit the floating point efficiency, even when intermediate constructions are called into play. To start with, let's see how a standard robust floating point predicate works. The predicate has some input values, these, that can be considered to be exact because, for example, they are read from an input file. Then it evaluates a polynomial expression, this one, on the input values, and finally compares the magnitude of the evaluated expression with the threshold and possibly switches to a more precise or exact evaluation. So this is, for example, how the famous predicates by Szuchak work. Well, an indirect predicate works similarly, but it also accepts implicitly defined input values. So these points here. So depending on the type of these implicit values, the polynomial expression changes, and so also the threshold value for the filter changes. So let's see what are these implicit parameters. An implicit parameter is an unevaluated expression on input values. So if a point has implicit coordinates, we call it an implicit point. For example, an implicit point can be at the intersection of two lines. So here, all these guys here are floating point numbers, but this point here is just implicitly represented. Okay. So the fact is that we want to write the expressions. I have no time to enter the details here now, but in most cases, we can write the expression of an implicit point in terms of polynomial fractions, as in this example. We have a lambda x, lambda f, lambda y, and everything is divided by this denominator d. And well, this is the core insight of my contribution. The idea is to compose the expression of the predicate with the expressions of its implicit parameters, thus leading to another expression, which is representable as a fraction of two polynomials. And well, to find the sign of such a fraction, we just need to compose the sign of the numerator and the sign of the denominator. So both the numerator and the denominator are expressions on input values, and hence can be filtered using classical semi-static filters. So in this case, we are using the intersection of two lines. Oops, sorry. And we are injecting this expression in the expression of the predicate, which is in this case the standard oriented. Then we just measure the sign of this lambda prime and d prime to know the final sign of the predicate. And all of this is exact if the filter succeeds. So having said that, this is how an indirect predicate is implemented. It is basically a cascaded evaluation of some expressions using different computational models. We start with floats, which is enough for the vast majority of the cases. But for the few cases where the filter fails, we switch to interval arithmetic. And if this fails too, we revert to floating point expansions, which guarantee exactness. Well, since coding predicates is tedious and error prone, I have also implemented a tool to produce the C++ code starting from the implicit points and predicates expressions. These are simple text files, including the equations. And starting from these files, my tool produces the for each predicate, the tool produces the floating point arithmetic evaluation along with all the semi-static filters, the interval arithmetic evaluation, the exact evaluation, which uses floating point expansions, and a multi-stage filtered evaluation that calls the previous three functions one after the other. So, to show the efficiency of indirect predicates, I have implemented an open source library, and you can find at this address here, whose API exposes a type called generic point. A generic point can represent either a 2D or a 3D point, which in turn can be further specialized to represent a specific implicit point types. The library also exposes a set of indirect predicates to work with these generic points, and can be used as simply as shown in this example. So we here have two explicit points. Explicits mean which have explicit coordinates. One implicit point, which is the intersection of this line here and this line here. This is our implicit point. And then we call this orient2d predicate on these 3 points. And this code correctly returns the fact that I is collinear with A and B without explicitly computing the coordinates of I. As a test bed, I used the standard Delaunay triangulation algorithm working on generic points. Okay, this image here is okay, it's corrupted, but you can understand it in any case. So in a set of 2D experiments, I generated random points, experiment 1, 1, random mixed points. So the red guys here are explicit F coordinates, the blue guys are implicit, are intersections of two lines here in this example because we are 2D, and uniform mixed points. Uniformity here is used to stress the encircled predicate during the Delaunay triangulation. Similarly, I generated a set of 3D points, explicit, mixed, and uniform. These are the three experiments here. And then computed the Delaunay triangulation on their projection on the XY plane. In this table here, you can see the time taken for the two experiments on explicit points only. I use these experiments to assess the overhead with respect to floating point coordinates. And in this other table here, I have run the other experiments while varying the amount of implicit points in the input. So this is the percentage of implicit points in this in the input one. And here you can see that the running time grows quite smoothly, and even the memory, this is the memory used in megabytes, grows smoothly. And finally, I have compared these results with Siegel on the same hardware. As you can see, indirect predicates are slightly slower when Siegel is used with exact predicates only, so no exact constructions, inexact constructions. And the overhead is, well, not really high. But it becomes much faster than the state of the art when exact constructions are necessary. So in the cases where we have implicit points. Here you can see that, well, the indirect predicates significantly outperform the state of the art. And this leads me to conclude. So what I hope to have shown here is that floating point hardware can be better exploited in geometry processing. Many important algorithms can take advantage of indirect predicates, and in the examples I've shown, when intersections are involved, indirect predicates are from nearly 4 to nearly 12 times faster than lazy exact approaches, while requiring up to 3.5 times less memory. Of course, there are limitations. Indirect predicates can be used only for constructions that are representable as fractions of polynomials. For example, if you want to construct the constrained Delaunay tetrahedrization of an input mesh using, for example, Schuchak's algorithm, you can't use indirect predicates because this algorithm requires some Steiner points with irrational coordinates. There are square roots involved. And it is not even an appropriate approach if many cascaded constructions are required, because in these cases, the expressions would quickly become very complex. And this would lead to large filters, which, well, would be not really useful because they will always fail. And finally, these indirect predicates guarantee that you can resolve the predicates without the need of explicitly calculate the coordinates. But in the end of the day, if the result of your algorithm needs to be fed to a downstream application that needs to read some floating point numbers, you need to actually calculate the coordinates of even the intersection points. And this requires to snap these coordinates to floating point numbers. And this is an issue because these little snaps can create self-intersections and many problems. This is actually an open problem. There are theoretically provable algorithms, but they are not really practical yet. They have exploding complexity for practical cases. So that's it. Thank you for questions, and thank you for your attention.
Thank you, Marco, for the great presentation. I seem to not see where the raise hand feature is, so and I don't know if anyone else has this issue, but if you have questions, either use the chat or speak up at the end. Any questions? Okay, I have one. Actually, can you maybe provide some examples of where you have been using this successfully to basically improve both the accuracy and speed of geometric predicates?
Well, example, we are currently using them in, will be presented in SIGGRAPH this year. We have implemented an algorithm to quickly compute whether a triangle is in the envelope of another triangle mesh. So to see if there are collisions or sufficient proximities. And we have developed this algorithm that creates local Minkowski sums of the single triangle. So these are some prisms like boxes that intersect with each other. And we follow the intersections of these query triangles with these prisms to know whether the triangle is in the envelope of the original mesh. And we use indirect predicates to know if these intersections occur actually and which are their topology. And we have verified that this speeds up a lot with respect to a naive use of, well, lazy evaluation, for example.
I see. So when you showed P1, P2, and P3, the two of them, you mentioned their explicit floating point. So does it have to be like that always, or could you have other combinations?
Oh, no. You can have any combination you want. The fact is that for any possible combination, you need to have a specific version of the predicate. That's why I developed this automatic code production, because you need many of them. If you look at the library, you will see that the API exposes just one predicate for each of the standard predicates. For example, for the Orient 2D, Orient 3D, the encircle predicate, and so on. But then if you look what that predicate does, it first discovers the type of each of its parameters. And depending on the type of these parameters, calls an appropriate version of the specific predicate. And this is necessary because each version has its own filter which changes depending on the combinations you can have.
I see. So you have really a systematic procedure to build these formulas that are maybe long depending on what the types are, but for every combination you can derive one basically.
Yeah, absolutely.
Okay, thank you. Does anyone else have any questions? Please just unmute yourself if you do, because unfortunately I don't see why I cannot see the raise hand feature today, although it worked in the rehearsal. Okay, I guess there are no questions. There is also Discord, another system where the video will be uploaded, and there will be, I believe, Q&A sessions enabled there. Okay, our next presentation. Thank you, Marco, again. Our next presentation is a sharp degree bound on G2 refinable multi-sided surfaces by Kęstutis Karšauskas from Vilnius University and Jörg Peters from University of Florida. Jörg, cannot see your screen yet. And you are muted. Jörg, I can see
Yeah,
your...
okay, so now you can hear me, right?
Yes, we can hear you. I can see only your background, I believe, which looks like Florida, but no presentation.
Yeah, I was just explaining that my university is still shut down, so I'm working out of my house, and so this is just a picture of my backyard.
Oh,
and you see, I can superimpose myself on this, and let's see how this works out. In terms of connectivity, I might just switch in the meantime from not showing my face to showing my face via a picture. Okay, so let me see whether I can share my screen with you.
Okay, we are...
And go back to the, why is this not doing what I wanted to do? It will eventually. There we go. Yeah, wonderful. Okay. All right, so I hope you can see the picture of both of the contributors to this talk. And thank you for the introduction. And it's a theoretical paper in many aspects, but it also has a very practical aspect to it. So this is a sharp degree bound on G2 refinable multi-sided surfaces. And I'm sorry, I have to push my cat away as we are speaking. She wants to actually look into the picture as well. But let me just do this here for a moment, and then the cat won't interfere in my talk. Good. So in design, of course, we need multi-sided surfaces to fill in holes by capping them. And you see on the right here some symbols overlaid on one 5-sided piece. These we will be using repeatedly later on. The center of this cap, the mid edges M, and the corner. And each 4 of them will form a quadrilateral, which forms a sector of such a cap. We also want to have good shape, and shape we can measure by not having oscillations in the curvature or by having smooth highlight lines, which are lights reflected on the surface from a fixed position. However, when we go to engineering, we want more. We want to have also the ability to increasingly approximate a function on the surface. So if we're solving a partial differential equation on the surface, the solution is typically not polynomial, and we need a space that increasingly approximates the correct solution. In other words, in terms of this picture, if we again look at one sector, what we want is that as we, for example, binarily refine, we want to be able to both keep the old surface and or function on the surface, but also allow ourselves to get more degrees of freedom to better approximate such a partial differential equation. And since we don't know where these new degrees of freedoms will be needed, we will want to have an increase of freedoms both in the interior and along the boundaries, whereby the green boundaries are the ones to the outside regular, and the red boundaries connect again to the central point that is marked as an O for origin up here, which is the central point of the cap. So this is, we say flexibility increasing because we actually need these extra degrees of freedom. We have one raised hand. I don't know whether I can easily, efficiently take care of this though. Sarah, I only got a flash here that said someone raised their hand.
Sorry, that was a test, I believe.
Okay, good.
Go on.
If you do, just enable it. So because I can't search around to find how to enable that. Okay, so we need multi-sided caps, we need good shape, we need increasing flexibility as we refine. And I don't know what is going on now, but here we go. Oh, this is my cat, sorry. Cat, go. All right, so it's really funny. My cat wants to program a little bit. So the key result of this paper is that for curvature continuous surfaces, any combination of biquintic, bi-5 surface pieces will not provide such a G2 refinability in a flexible fashion. So we will not gain additional degrees of freedom as we invest into having 4 times or 16 times as many pieces of degree bi-5. However, for bi-6, there is such a solution, and they are not only flexibly refinable, that solution, but also produces good shape. Together, this means that we have both a lower bound of what allows us to be flexibly G2 refinable, and an upper bound in that we have a construction that actually allows us to flexibly G2 refine a given surface and functions on those surfaces. And that gives us this sharp degree bound on G2 refinable multi-sided surfaces. Okay, there's 3 parts to my remaining presentation. First, the setup. Here we see what is called an extended CC net. CC is for Cutmore-Clark. It reminds of the basic setup that we have there. And we notice that these extended nets are large enough so that we can have groups of 4x4 vertices in this grid. And each vertex you can think of as being a generalized B-spline control point. We extend this so that we can create a regular bicubic boundary around the central part that we're interested in, the multi-sided surface. To be a bit more precise in detail, if we think of the points, the 4x4 points here, as being the B-spline control points, then by some technique called knot insertion, we obtain the Bezier control points, which define a single polynomial piece. And so as we compute these single polynomial pieces for one quadrilateral at a time, we sweep out this bicubic ring. And the places where we do not have the next layer, because we have an extraordinary point and we go beyond, at this point, at least we can convert 12 B-spline control points into 12 Bezier control points. And these extra Bezier control points that we see here, we can look at as being along a border or boundary, as being the Hermite extension up to 2nd order into, well, into this piece here now. And we can see this tensor border, because it has a tensor structure, it is a tensor border. We can see this tensor border here attached to this green outer ring that is just regular. So for the cap construction, we actually use only this tensor border, and this tensor border is well defined by the CC net, not the extended CC net. The extended one we only need to describe the surface surrounding it. So this is the first of 4 parts of the setup. The second idea here is change of variables. This T up here stands for the tensor, the tensor border, and the rho is a change of variables. So the rho actually, when we go down here, the rho consists of 2 maps in 2 variables. So it's a map from R2 to R2. And we see here we're along the U axis at the bottom and then expand. And if we look at this tensor border here, it's of degree 3 in this direction of degree 5. So what does this change of variables do for us? Well, it can change how we expand our tensor border. From a degree 3, we go to a degree 5 tensor border, and that's a typical technique that is being used to create these surfaces. In fact, when the term G2 just means to change, to compose with a reparametrization rho, and then match the derivative. So the G2 constraints between two surface pieces is just that. It's a change, it's matching derivatives after change of variables by rho. And we can write these out in some more detail. What is interesting to remember here is that we have these scalar valued functions A, B, D, and E, no C in here because that's for cosines. So A, B, D, and E are the scalar valued functions in U that define this change of variables across boundaries. Third component, we will be looking at many pieces potentially, all of degree 5. You can count here 1, 2, 3, 4, 5, 6. Each one of these small regions here is the control net in Bernstein-Bezier form of degree by 5. And you see that they become slightly dashed in the limit because you might have many, not just 16, you might double that again and double that, or quadruple that again and quadruple that again. The proof that will come will say it doesn't matter how many of these pieces you have per sector, you will not succeed in getting a refinable construction that is G2 everywhere. Now, we will only look at reasonable constructions. And what does reasonable mean? Reasonable means that if I have a construction formula for one of these coefficients here with a subscript ij, and I look at its counterpart ji across this diagonal, then I should get the formulas for constructing ji by taking the formulas for ij and replacing every I with j and every j with I. This is called diagonally symmetric. That is invariant under reversal of the indices. And any reasonable construction would have that property because otherwise just feeding in your data in a different order would create a different surface. Similarly, it shouldn't matter what label I give this particular sector or whether I'm looking at the left or the right sector, I should have similar construction formulas. Note this is not that the geometry is symmetric, it's that construction is symmetric. Final assumption for reasonable G2 constructions is that the sectors should be internally C2. So all of these transitions between by 5 pieces should be smooth, matching derivatives without change of variables. There are several reasons for that, but one being that we're going to refine this structure, and this structure has, being polynomial in pieces, has many transitions that already must be parametrically, without reparametrization, differentiable. So all these transitions here will be C2, not G2 internally. Third component, what is flexible C2, G2 refinement? Well, here we see again, internally C2 across the boundaries will have geometric continuity, so continuity after change of variables. And there's both the green to the outside and the transitions between the sectors in red. And what we now do is a binary refinement. And as was mentioned before, because we want to use this to modify or improve an existing solution, we should always get additional degrees of freedom, not just in the interior, but along any of the edges. And the main proof for a lower bound will show that for biquintics, you cannot achieve that. Okay. So here is the proof, not quite in a nutshell, but almost as short as possible. Again, the lay of the land, this is the outside, this is sector separating curves. And we now look at the green part, which connects to the outside. And we have here again the tensor border and a reparametrized tensor border. And the proof is mostly about the reparameterizations. The first part of the proof shows that these functions a, b, d, e that we had in the reparameterizations that are scalar valued must all be polynomial functions. They cannot be, you say everyone is, and anyhow the surfaces are polynomial, so a, b, d, e might be polynomial, but they could be rational. What we are doing here is we are excluding the possibility that a, b, d, e are rational. So they must be polynomial, and it's in a way an elementary proof, but you have to be careful in how you phrase it. And it's in Appendix C if you wanted to read that in the paper. Once we have ABDE polynomial, we can actually give degree bounds. This is a very classic approach to relate the degree of the polynomials that are outside and inside this multi-sided surface to one another. It's an algebraic proof to give us a bound on the degree. And then when we add the reasonable assumption of internal C2 and the requirement of refinability, we find that not only is the degree bounded, but in fact, B, D, and E are just 0, and A is the constant 1 function. And this means that for degree by 5, our reparameterization across the boundary into this multi-sided cap actually is the identity. It will change from degree 3 to degree 5, but that's just raising the degree. It doesn't change the actual parameterization. Similar argument shows that the function, the sector separating curve, is up to first order effectively also the identity. Well, it's the flip identity because it relates left and right parts, two sectors with respect to one another. And so here the B is polynomial and the A is fixed to be -1. So here's slide 2 that will give the whole proof. We start out again with our regular setup and we focus on one of these M's, which are the mid-edges. And at the mid-edge, because our parameterization across the green line had to be the identity, it means that we have regular C1 constraints, which means of any triple, the middle point is the average, exact average of the two outer ones. And this is true for degree, for an expansion 0, 1, 2 across this outer boundary. The tensor border has to be the identity. But now we can leverage the second result, which was on the red reparameterization, which then forces this C1, strict C1 constraint to percolate up in the direction of the extraordinary point, percolate up, and again give us strict C1 constraints. Now comes the reasonable assumption that we have a C2 transition between each one of these internal pieces, and that extrapolates the same pattern further towards the irregular point. And in the end, we have a conflict at the extraordinary point because we're supposed to be creating these straight lines of Bernstein-Bézier coefficients, which means C1 constraints, but in the limit at the irregular point, this is not possible. So there cannot exist any construction of degree by 5 that actually works with irregular points. The converse construction, an upper bound, is in some sense can be made much shorter. It's actually a very nice construction that we'll see, but
Jörg, it's almost time, so if you could wrap it up in 1
Are we
minute
at
or
15
so,
or at 20 minutes?
Great.
No, are we at 15 or at 20 minutes?
You are at 20 right now.
20, okay.
But,
fortunately,
yeah. We would like to leave some time for questions.
Right. So,
Thank you.
The interesting part here is the structure of this construction, of many of whose examples you see on the right, and the degrees of freedom. The degrees of freedom across this green boundary are exactly those of refining the B-spline across. The interior ones are those of C2 by quintix. At the center, we have a cubic expansion. And so the only parts of interest is that usually is a big mess is how do we get additional degrees of freedom along these sector separating curves? And here the beautiful solution is that the sector separating curves have to be degree 5 and C4. So this is a spline. The degrees of freedom are those of a spline that is maximally smooth and of lower degree than the rest. Similarly, the next is a C3 degree 6 spline and a C2 degree 6 spline for the next layer. And so this concludes my presentation. We saw that biquintics are not flexibly refinable, bi6 are, and so we can have geometry suitable surfaces that are analysis suitable. This is the bi6 ones, and conversely, we have analysis suitable that are also have good shape and are geometry suitable. Thank you.
Thank you, Jörg. We have time maybe for 1 or 2 questions, quick questions. If you see anyone raise their hands, you can take them, Jörg, because I can't see it.
Okay, I see no hands either, but let's see, we have the more disabled.
Can you maybe briefly talk about how this can be used in for physical analysis, or can it be generalized to 3D, to volumetric setup?
Right. So the first question, how you would actually compute with this, is not explicitly covered in this paper, because this paper gives a theoretical fundamental result on one hand. You cannot do better than. You're now asking for how can the bi6 surfaces be used because they are refinable? And the answer is, if you wanted to compute your differential equation on, let's say, this steering wheel shape, what you would do is you would apply the technique of isogeometry, or inverting the geometry representation and composing it with a deformation function, and you would be able to compute, say, heat or deformation on this particular steering wheel. Intentionally, this is not covered in this paper because those are true related, but it would lead away from the main purpose of this paper to discuss that in more detail. Three-dimensional, there's very few techniques at this point that map. Well, first we have to be sure what we mean by that. Presumably we're talking about trivariate maps into trivariate space, because these here are bivariate maps into trivariate space, obviously, they're surfaces. So this particular technique at this point, the difference between what you can achieve in trivariate and bivariate is still very, very large. It's very difficult to take reparametrization into the third variable. There are some attempts at this, but it's really just rudimentary. There is at this point one solution which works with an explicit singularity but gives you C1 trivariate. But again, this leads away from this particular one. Basically what this paper tells you is don't ever even try to, if you need refinability, of course you want reflexible refinability, otherwise you don't gain anything. You can just, subdivision so you don't gain anything unless you have flexible refinability. If you want that, don't even try to construct a scheme that uses polynomials of degree by 5.
Thank you, Jörg. Okay, The next presentation is on maximal disjoint ball decompositions for shape modeling and analysis by Jiangche Chen and Horia Elias. If you could take over the screen, that would be great.
Okay. Hi everyone, can you see my screen?
I think we can still see Jorg's as well. Jorg, can you turn it off?
How about now?
Oh, no, this is good, yes.
Yes, good, okay. So good morning, good afternoon, and good evening. And I'm Jiangche Chen. I'm a PhD student from University of Connecticut, and my advisor is Horia Elias. And I'm honored to be here to present our work, maximum disjoint ball decomposition for shape modeling and analysis. And over the years, in different steps of product development, researchers have established specialized representations to support specific downstream applications. Like we have nerves as a golden standard for model creation and adding, and some researchers use level set in V sublimes for cellular material representation. And we have spherical decomposition for collision detection and motion planning. However, at the same time, we are seeing more and more applications that need to handle different representation together. For example, in Industry 4.0, people are expecting that to combine the stages of design, simulation, and manufacturing deeper with artificial intelligence. However, one of the largest obstacles in the past is that we are using different representation in these stages, like meshing a completed boundary representation model in design stage for finite animated method is always a problem. And in augmented reality or virtual reality, there are many models coming from different sources, including various meshes in dataset and many point cloud models scanned by depth camera. However, we still don't have a good method to measure the similarity between models in different representation directly, because all the shape descriptors we are using now are representation specific. It means that they can either working on one representation or they cannot guarantee consistency across different representations. And conversion between different representations is non-trivial. It's time consuming and it involves information loss, and often it requires manual interaction. So we think one promising way is to build a uniform framework that covers most of the representation we are using today and support as many applications as possible. To build such a uniform framework, we'll need a good shape descriptor that has at least such three characteristics. The first is generality. It means that the shape descriptor should be built based on an attribute that is shared by most of the representation we are using today. And the second one is uniqueness. It means the mapping between the mathematical model and the shape descriptor should be one-to-one mapping. And it will save a lot of work for equivalence check. And equivalence check is especially critical when we're dealing with models in different representations. And the third one is stability. Such shape descriptor should be stable against small boundary perturbations, so we can build a continuous similarity measurement based on it. And we noticed that the ball decomposition has been studied for a long time, and many methods and applications has been developed on it. Like we have like quadrilateral meshing by circle packing, and the method of finite sphere, a kind of mesh-free method to solve boundary value problem, and inner sphere trees for collision detection. Because of the versatile form and multi-usage of ball decompositions, we think both conditions could be used a good candidate as a shape descriptor of the framework we talked before. However, current both conditions are not unique. So in this research, we're trying to define a unique both condition. So here is a simple idea, and more details are covered in the paper. So given such a domain, we first place the largest circle inside the domain, and then we update the domain by cutting the circle from the original domain. And in this new domain, we place the larger circle contained in it, and we continue the iteration until the latest circle radius below a threshold. So in the end, we will have a unique set of circles that decompose the domain. And we found that during these calculations, we only need to know the distance function of the domain. And in every step, we found the maximum of the distance function. And distance functions has to be supported by any valid geometric representations. So such decomposition process has generality characteristics. And we found such decomposition also have hierarchical structure, that the details of the domain are captured progressively during the process. And it gives us a convenient way to control how many features we would like to cover in real-time analysis. And we also got two data from the decomposition that contains the geometrical information of the domain. One is a radial list that consists of the radii of the circles in every level. And the other is a graph that captures the tangency pattern between the circles. And we will use these two data for shape analysis later on. And for some other cases, we might have multiple maxima or distance function for the domain. Like in these cases, this domain has two maxima for its distance function. And consequently, we will end up with two decompositions. So now we will need a kind of standard to choose unique decompositions if we have multiple choices. And so we apply lexicographic ordering to order decompositions. Just like we order the words in dictionary, we order the circles in the decomposition level by level. And we found that the circles in the first two levels are equal. And in the third level, A3 is larger than B3. So we conclude that decomposition A is larger than decomposition B. However, in some cases, if we have infinitely many maximum choices, we cannot easily just list all the possible decomposition and find the largest one. Like this rectangular domain, the maximum of its distance functions are the middle segment of its medial axis. And we observe that if we place the first circle at the branch point of the medial axis, we will always get a decomposition that is larger than other decompositions. Like in this example, we can see that C2 and D2 is larger than B2. So we reducing the infinity cases to the finite many maxima in the that is in the last slides. And now we got two decompositions, which that in every level they have same circles. It seems that the uniqueness is broken up, but actually they are the mirror reflection of each other. So they are the two decomposition in essential. So the uniqueness still holds. Here's the definition of the maximum disjoint bottomization. And so the MBBD is the maximum of this ball decomposition for the domain, and based on the lexicographic ordering. So the uniqueness of MDBD come from the maximum in its definition. Now let's talk about the stability. As we know, the media axis is unstable against the little boundary perturbation. Like in this case, a little perturbation on the boundary will cause many unwanted branches on media axis. However, the value of the maximum or distance function are relatively stable against the boundary noises. So MDBD is value could be more stable against the boundary noises than media axis do. And it was illustrated more on this lower picture. Here we gradually glow this feature on the boundary, and we found that the layout of the circles in other places are still unchanged all the way. So MDBD, so the little boundary noises have only a local effect on MDBD. However, in some special cases, MDBD could still be unstable. Like this rectangular domain we have is as an MDBD in this picture. If we add little noises on the upper boundary, like in here, then we will find that the circles at the middle of the media axis can be larger than the circles. So is there someone raise hand? But I don't know. Okay.
You're good.
Okay.
I think you, yeah.
Okay, I will continue. So in this case, the layout of the media, the MDBD will change significantly. We would like to say we still need to study further on this issue, but at least what we can see now, we can deal with, we can redefine MDBD along the approaches like lambda media axis or ipsial topology that people use to redefine the media axis. Okay. And here shows the result of our algorithm that computing the MDBD for point cloud model and the boundary mesh models. And the core part of the algorithm is to compute the sign distance function, which is SDF of the domain, and update the SDF every time when we calculate a new ball inside the domain. And it is time consumption and the configuration of the computer. Now let's see what can we do with MDBD. So we can use a graph to capture the tangency pattern between the balls inside inside the MDBD, and then we can use graph analysis tools to process shape analysis on the domain. And one advantage of graph analysis is that its result is environment with rigid body translation, scaling, and mirror reflection. Like in this case, after this circle assembly rotated, its contact graph are isomorphic. And here we use a simple method called random walks on the graph to extract the features on the graph. And we use the result of the random walk as a feature vector for the domain. So the similarity distance between two domains will be defined as the distance between their corresponding feature vectors. And we evaluate our similarity measurement on a subset of co-stage dataset. And in this dataset, we have 4 classes of models. And in each class, we have a query model in point cloud and 10 other models mixed with point cloud and boundary meshes. So here we have a heterogeneous data set. And here's our result. On the left, the up left picture is a query model. And the bars, and here we have 40 bars. And the height of the bars are the one model. The distance, similarity distance with one model against the query model. And here the this lower picture is the model that has the smallest similarity distance with the query model. And as we can see, the results are consistent with human intuition. And on the right, we see what happens if we add noises on the query model. And as we see, the pattern of the distance distribution haven't been changed significantly. And it shows that the MDBD is stable in practice. And in this experiment, we show that the graph of MDBD can be used directly for shape classification. And we built a deep learning neural network to extract the features from the graph. And here we used a graph convolutional layer, which can process directly on graph data. And we evaluate our neural network on a benchmark dataset called the ModelNet 10. And the results are shown here. And we can see that our model accuracy is comparable with other models. And while others can only work on one specific representation, but ours, since we work on the graph of MDBD, and MDBD supports any valid geometrical representations. To sum up, here we propose maximum disjoint ball decomposition, which is a pax of maximum disjoint closed balls inside a d-dimensional domain, and it only requires distance computations, and so it must be supported by any valid geometrical representation. And we show that it's unique and stable in practice against the small boundary perturbations. Actually, especially it is stable for domains whose distance function has finitely many maxima, and it can be redefined for domain whose distance function has infinitely many maxima, and it can be used to define universal shape descriptors, and it supports downstream application and heterogeneous models. And we want to make our acknowledgement to Financial Science Foundation for financial support and anonymous reviewers for their constructive feedback. And I would also thank you for all you listening. Now I'm glad to take questions from you. Thank you. Yeah.
Thank you, Jiangchen. Any questions? I have one actually, or maybe two. Can you, do you have slide 17, I think, or 18? 17. I think 17 when 17? You're comparing, yes. Can you explain what each one of these columns are?
Do you mean the right one or the, or the left one? The right one?
Either of them. Either of them. What does the right of each column represent?
Oh,
I missed that.
Okay. In the left one, the columns are so the x-axis are the 40 models I showed before. This is this 40 models, and this is for the query model, and this is with other model. And in each, the height of the column is the similarity distance between the one model against with the query model. Yeah, and we then find the model corresponding model that has the smallest distance from this similarity distance with the query model, which is shown here. And on the right one, it has, for each model, it has 3 columns. And one is no noise, and the orange one is at 0.5% noise, and this percent is percent of the smallest circle that covers the total model. It's the diameter of the circle covers the total model, and it was implemented in MATLAB, and the other one is 1% noises.
Okay, I got it. So then on the, for example, for the 2 peaks at the top left,
yes,
the match is the third model, right? The smallest
Yes.
distance on A, but then there are other matches, I mean, similar distances for other models. And then it seems like with noise, you actually can get the wrong answer, right? Am I
Yes.
reading this correctly? Because I see that the shortest columns are actually, there are multiple shortest columns in your first plot on the top left, or other plots as well. Like for example, for the iron,
Yes.
there seems to be 4 matches. I mean, 3 matches other than the top one.
Oh, yes.
And with noise, you could actually get them to have a lower score.
Yeah, actually, yeah, I didn't show here, but actually when the noise is added, this, if you zoom in, you'll find that these shortest columns are all belong to the iron classes. So at the noise,
they do.
so
Okay.
yes, at the noise, they may be not be this specific iron, maybe some other iron. It could be, yeah. But they still belong to the iron classes. Yeah.
Okay. And have you tried maybe comparing this to other descriptors that would be unique? For example, you could, I mean, I think this is done a lot in protein analysis literature, that they take arbitrary surfaces and do harmonics on them. For example, the first, whatever, 10, 15 modes would be your shape descriptor, and probably unique up to some transformations as well.
Yes, they do. They are such shape describer, but this shape describer cannot work on heterogeneous data sets. So as we know, so this kind of first method that can work directly on heterogeneous method. And we still don't find such data set, such benchmark data set that can compare the method together.
By heterogeneous, you mean in terms of representation?
Yeah. Yes, the representation consists of different representation. In here, it contains point cloud and boundary mesh models. Yeah.
Okay, thank you.
You're welcome.
Do we have any other questions? Okay, I guess this concludes our session. Thank you everyone for joining, and enjoy the rest of the conference.
Thank you.
Bye.
Bye.
Bye. Bye.